Okay, there are a couple of exercises after the K-maps, but you can try them if you want, but I'll prefer to solve them during the live lecture. So I'll skip those and jump to section 6, NAND and NOR implementations. Now, NAND and NOR circuits, because of their transistor level implementation, it's actually the starting point for other gates, like AND and NOR gate. I will quickly demonstrate how this is happening with the transistor level. So let's say we have got VDD line on top, and we have got two transistors in parallel, which they are PMOS transistors, and two transistors in series. Okay, so this is connected together, and these two inputs are connected together. Let's say this is A, and let's say this is B. So two way of implementing it, and this is the ground. Okay, so this is two PMOSes in parallel and two NMOSes in series. Now, when we consider that when the PMOS gate is 0, it turns on, and when the NMOS gate is 1, it turns on. Let's say we have got the capacitor over here. Now, what do we need to know? This is, let's say, F. When A is 0 and B is 0, the first condition, what will happen to the F? Let's check that out now. So when A is 0 and B is 0, that means A is turned on, the PMOS transistor, B is turned on, and NMOSes are off. Or let me put these down somewhere that I can erase it easily. These are turned on, these are turned off. Now, this means that the VDD charge can either go through this path or through this path. So we are actually charging the capacitor, and output is going to go from 0 to VDD. Okay, so that means output is going to be 1. This is the first one. Let's say I want to keep A 0 and B as 1. So at this point, A is still on, B is PMOS is off, B NMOS is on, and A's NMOS is off again. Now, we still have a path that can charge the output. Also, it can go down over here, but it's not going to go to the ground because this one is still off. So there's no path to the ground. So we still have a charge, and the output is 1. So that means when it is 0, 1, we have got an output 1. Let's try another way around. So 1, 0. Now, PMOS is off, NMOS is on. Sorry, B PMOS is on, and B NMOS is off, and A NMOS is on. Now we still have a path to the output, and there's no path to the output from output to the ground. So that means this is still 1. So that means 1, 0 is also giving us 1. And let's try the last condition, which is 1, 1. When it is 1, 1, these two PMOSes are off, these two NMOSes are on. and nothing will charge the capacitors, but the charge on the capacitors will be discharged to the ground. So that means 1-1 condition will be 0. So what's this function? This function is opposite of AND, which is known as NAND function. Okay. Now, as you can see as a transistor level, when we implement a NAND gate, we are using 4 transistors, 4 these. If you want to implement an AND gate, you have to add an inverter to the output. So that this is ground, this is VDD. So this output has to be connected over here, and you have got, let's say, function G or X, let's say, and that X is actually A dot B prime prime, which they are going to cancel each other, so X is equals A dot B. So it's a AND function. So the base of AND is actually NAND. And the base of OR is actually NOR. So in order to get a NAND AND gate, we have to implement NAND gate first. In order to implement OR gate, you have to implement NOR gate first as a transistor level. Now, NAND and NOR implementations, they are actually quite useful because you can implement any kind of circuitry with NAND and NOR implementations, and they are universal. So why are they universal? Let's say NAND function, once again, we have got an inverter. What do we know about inverter? A and Y. When A is 1, Y is 0. When A is 0, Y is 1. This is what we know about inverter. So, by using a NAND function, NAND gate, can we implement an inverter? Can we implement an inverter? Yes, we can. So how are we going to do that? Once again, I'm going to put down the NAND function, truth table. We know that it's opposite of AND, so they're all 1 except the 1, 1. Now, in order to get invert, I have to look at one thing. When the input, as I have got one input over here, this has to be one input as well. So when input is 0, output is 1, and when input is 1, output is 0. It has to satisfy that condition. Now, when you look at the truth table, we can actually easily see that this line and this line is satisfying that. Because when A and B are zeros, output is 1. When A and B are 1s, output is 0. So in order to implement an invert function with NAND, I can have an inputs which are tied together or equivalent to each other. And I can say this is A and this is Y. So when this is 0, this will be 0, 0, 0 will be 1. Or alternatively, when this is 1 and this is 1, this will be 0, based on the NAND function truth table. So we can implement an inverter using NAND gate. How about AND gate, which I already mentioned AND gate. So if you want to implement an AND gate using NAND gate, the properties are similar. So all you need to do is implement a NAND gate And we just need to get rid of the bubble in front of it. So we just put an inverter over there. NAND gate with an inverter will give us AND gate. So if you take the complement each of those or invert it, that will give you AND gate. And lastly, we can also use a NAND gate and implement a OR gate. So OR gate, either of the inputs are 1 or both are 1, output is 1. So OR function ABF 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 1, 1, 1 if either of them. Now the NAND function want this again 0, 0, 0, 1, 1, 0, 1, 1, and this is F 1, 1, 1, 0. Now, if I want to implement this function using this function, I just need to make some modifications to my NAND gate. Now that modification is, when you look at it, it's going to be 1 in all cases, right? So when you think about the function itself, which is NAND function is A, B prime. Now, if you take the De Morgan of that, this is going to be A prime plus B prime, right? So we have got an OR gate over there already when you take the De Morgan of the NAND. So the only missing part is this is A prime and this is B prime rather than A and B. So in order to have A and B's over here, I just need to take the complement of those and feed into the NAND function. So at this point, this is going to be like A prime dot B prime prime. So this is, if you take the De Morgan of that, this becomes A plus B. That's it. So we can implement an OR function using inverters for each input and the NAND gate. Now, as you can see, inverter and OR functions are all implemented by just using NAND gate. So this is giving you a chance to have more compact and more modal and more efficiency in order to design it, because you can just use the same kind of cells and you can implement the large functions. So NAND gate has got two symbols, A, B, and F, which is F is equals AB prime, which we call it AND invert NAND, because we are doing AND gate and then we are doing invert. The other one is an OR, but it's inverted OR. So let's say X, Y, Z, and this is going to be F, and F is equals X prime plus Y prime plus Z prime. And why is that happening? What is this alternative? This is actually coming from F equals X dot Y dot Z prime, which is the NAND function. If you take the De Morgan, this is what you are going to get. So you can implement it this way, and we call this invert OR function, because we are doing the invert and then we are doing the OR implementation. So two graphic symbols for NAND operation. And these are also mentioned in the first slide of the NAND NOR implementations. Inverter, AND function, and OR functions can all be implemented with NAND gate and the symbols for it. So how are we going to use this? Let's say we have got a typical sum of product A, B, or C, D. Now, if you do a typical implementation, you just need AND functions. And those AND functions are ORed A, B, C, D, and this is F. This is a typical sum of product implementation, which we haven't used NAND gates. Now, if you want, we can use NAND gates, and we can convert each AND gate to a NAND gate. And OR gate either as a invert OR, and we can combine those, or we can have all of them as AND inverts as an AND implementation. So A, B, C, D, F, A, B, C, D, and F. Now, let's see if we are going to get the same equations. This is A dot B prime. This is C dot D prime. So this prime, it's going to be a prime, and this prime, it's going to be a prime. These are going to be cancelled. These are going to be cancelled. So F is going to be AB plus CD, which we are getting the same result as this. Then over here, this is A dot B prime. This is C dot D prime. And of course, we have got F, which is A dot B prime dot C dot D prime. And we have got prime on top. So we are actually taking the complement of those because that is going to be cancel that one, and that becomes plus. So we have got A, B, C, D again, and they are all giving the same answer. And this is the NAND implementation of a typical sum of product. Okay. Here is an example. Implement the following Boolean function, f. Simplify the function in sum of product forms. Let's do that. It's 3 input function, so we need to have 8 squares, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and that's going to be x, y, z. So minterm 1, minterm 1, minterm 2, 3, 4, 5, and 7. And the other ones are zeros. So the combination, I can combine these 4, which is going to give me x is changing, y is changing, it's just z. And then I have to do these two, which is x and y prime. And of course, I can combine these two, which is going to give me x prime y. So I can say that f is z or xy prime or x prime y. Now this is the sum of product that I am getting in the end. I can implement this circuitry using logic symbols. If I just use AND functions, this is like x, y prime, this is x prime, y, and they are all OR together with z, and this will be f. So this is typical sum of product. Now, if we want to implement this with NAND gates, once again, AND gate, it's going to be a NAND gate, AND gate, it's going to be a NAND gate, and OR gate, invert, we need 3 inputs, invert OR, which will give us F and Z. This is X, Y prime, X prime, Y. Now let's check if this is going to give us the same expression. So X, Y prime, prime, X prime, Y prime, and Z. Now because of that, this is going to be another prime, and for those as well, prime, and this will be prime. So in the end, F is going to be, these are cancelled, these are cancelled. F is equals X, Y prime, or X prime, Y, or Z prime. Now, the thing is, this is Z prime, this is Z. That's the only difference. And this is because the invert over here. Now, if we are having a single variable, which is not going into any gates, and if it's going to be inverted, I have to modify this input. And I have to put another inverter over here. So when it gets there, it's like Z prime, prime, which is ending up in a Z. So we can just have Z over there. Okay, so that's modification is required. And we can also do the same implementation using all NANDs and inverts. They're all NANDs actually. So and invert, and this is going to be X, Y prime, X prime, Y, and Z. Now, X, Y prime, X prime, Y, and Z over here. So F is X, Y prime, dot X prime, Y, dot Z, and then prime. And this will end up X, Y prime, prime, plus X prime, Y prime, plus Z. Now, the thing that we are getting here, I forgot something over here. Hang on. If I go back, I forgot to add the other primes. So xy prime, this is prime, and this is primed because of the AND invert. So xy prime, prime, dot x prime y prime dot z, and then prime because of that. So this is actually going to cancel that one and put a prime over there. So x, y prime, or x prime, y, or z prime is the answer. Now this is z prime again. So that means I have to modify that as well and add an inverter here to make that one as primed, and then that prime will be cancelled over here, and we don't have any prime in the end. So these modifications are actually can be done. So the K-maps and the implementations. Now over here is Z prime is used rather than an inverter. That's also acceptable if you are doing this while you are feeding in as a inverted version. So the procedure is simplify like we have done it in the form of sum of products, draw a NAND gate for each product term. Okay, so we've done the simplification when we draw the NAND gate for each product term. And the inputs to each NAND gate are the literals of the term, the first level. A single NAND gate for the second sum term, the second level, which is this one. A term with a single literal requires an inverter in the first level if the single literal is not complemented. So we need an inverter over there. So all the procedure is actually followed in our example, and we can easily implement it. So general procedure that we need to follow: convert all AND gates to NAND gates with AND invert graphic symbol. This is AND invert graphic symbol for all AND gates. Okay, and convert all OR gates, if you are doing a NAND implementation, as invert OR function. Okay, so check all the bubbles in the diagram. For every bubble that is not compensated by another small circle along the same line, so complement cancels each other, insert an inverter, one input NAND gate, or you can just complement the input literal like they have done it in this example over here. They just used Z prime. So these are the general procedures that we can follow. And you can see some examples as well, like AB prime or A prime B, which are these two. They are OR together, and then it will be ended with C or D prime. Now, what we are taking care, each AND gate is changed to converted to AND invert, and an OR gate is converted to invert OR, and invert. So in the end, we have to make sure that we are getting the same expression as AND OR gate as NAND gate. Now, NOR function is the dual of the NAND function. So it's also universal. Now, I can just show you the same examples that we have done for the NAND. They can be applied to NOR as well. So inverter gate, we can also implement it with NOR by tying two inputs. Okay, so it will give you the same result. And implementing OR function. So to implement an OR function, we just need to add an inverter to it, like I have demonstrated with the transistors, to get rid of that bubble. So these are going to cancel each other, and you will end up with OR function. And AND function to implement with OR gates. So to implement with NOR gates. Now NOR gates, and like we have done it, so AND function is A dot B. Now, when you have an OR gate with a NOR gate with A plus B prime, when you take the De Morgan order, this is going to be A prime dot B prime. So you're actually having an AND function over there. We just need to get rid of those primes. So that's why we add inverters again to the inputs, which is this is A and this is B. And that will be F. So that's also equivalent. So adding an inverter in front of it will give you the same approach. Now, NOR gate also has got two way of symbols. It's OR invert, or invert, and the F is A plus B prime. And then we also have invert AND. A, B, and F. So invert AND also does the same thing, which is going to be A prime dot B prime. Okay, so this is actually giving you the same answers. So you can see an example over here. NOR gate. So everything is implemented with NOR functions. That's E prime, and that prime is cancelled. And implementing this one, so there's an AND function. You can just use invert AND again, and OR functions are just using OR invert and OR invert and invert AND in between those. So that will give you the same result as this expression by implementing NAND and NOR implementations. Okay, so if you have any questions or if you need to understand how these are working, please just revise and you can ask me. As I said, they are more compact to use NAND than NOR implementations. So in the exam or in the homework, I might ask you to implement this using only NAND gates or using only NOR gates. Okay, so the last part of this chapter is about exclusive OR functions, which we already said that XOR is an odd function. Okay, so ABC 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And let's say F, so exclusive OR A, B, and C, and F. And we also have exclusive NOR, which is inverted version of it. Let's say G for that. A, B, C. And this is for odd, this is for even function. Now, odd function, we are looking for odd number of ones in the inputs. 0, 0, 0, it's 0. 0, 0, 1, 1 is odd. There's only single one. Single one, two ones, it means even. Single one, two one, two one, three ones. So odds and evens are identified. And G, which is XNOR, is actually even function. So 0, 0, 0, it's 1. 0, 0, 1, it's 0. 0, two ones, that means it's even. Odd, two ones, even, even, and odd. Or you can see the relationship. They're just inverse of each other. Okay, so this is how we can show them on a truth table. Now, exclusive OR functions, either 2 inputs or 3 inputs, they have got a symbol X plus inside of a circle, and this is XOR, XNOR, dot in a circle will give you XNOR. So odd functions, even functions, or in XNOR it's equivalent function. Same identities as Boolean algebraic that we have seen. So X XOR 0, it's going to be X. You can try that. So X XOR 0 means X can be 1, 1 XOR 0, it's going to give you 1, which is X. 0 XOR 0 will give you 0, which is again the X. X XOR 1, it's going to be X prime, which is opposite. X XOR X is 0. So 1 XOR 1 is 0, or 0 XOR 0 is also 0. X XOR X prime. So X, let's say 0 XOR 1 or 1 XOR 0 will always going to give you 1 as it is odd. And having a prime in any of the variables, this is also looks like an XNOR function. Okay, and the same applies for if you're having a prime as X, then it will repeat and it will get you to XNOR function as well. XNOR is also commutative and associative. Whatever the way you write them, you are going to get the same answer. No matter how many inputs you have got, you can replace the parentheses and you will still get the same results. And once again, you can use AND or NOT gates and implement it, or you can use NAND gates because the expression is x prime y or x y prime. So 0, 1 or 1, 0 in the truth table. And you can use inverters and AND gates, inverter AND gate, inverter AND gate, and OR them together. And that can be implemented with NAND function as well. So XOR with 3 or more variables can be converted to an ordinary Boolean function. So like we have said, replacing the XOR symbol with its equivalent, which is this one. 3 functions or 3 variables or 4 variables will actually give you the same thing. So the where we have got some of the minterms as 1, minterm 1, 2, 4, and 7. These are given here. And the Carnot maps, as you can see, you cannot combine any of the ones with each other. This is the property of exclusive OR and exclusive NOR functions. No matter what you are getting, they cannot be combined with anything else. So you have to write each of these minterms. So this is like x prime, y prime, z. This is x prime, y, z prime. This is x, y prime, z prime. And this is x, y, z. Okay, so this is exclusive OR. And exclusive NOR is similar, and you cannot combine them with anything else either. So 4 variable, still similar. All of the ones are coming to a point that they cannot be combined with anything else. You can have all the expressions written down. You need a 4 variable, 16 possible combinations, which has to be mapped, and they cannot be combined with anything else. So exclusive OR function generally used in the parity bits. So parity generation that we have seen in ASCII codes, X exclusive Y exclusive Z, and parity check is just using the inputs and the parity bit to check it. Now, if the check bit is 1, that means 1 bit error or an odd number of data bit errors. If parity check is 0, then correct or an even number of data bit errors. So that's all for this chapter about universal gates and NAND and NOR and exclusive or exclusive NOR, which are used for odd and even functions. Thank you.